Now, the question is, what is big data? A simple definition is, if the data cannot fit on a single computer with the memory that it has, then what do? First, I have to fit the data in multiple computers. There are two options that I have. I have 100 million records, which is, let's say, 5 terabytes of data. Okay, I want to do a machine learning. It's a mega Excel monster, like 180 columns, 100 million rows, and then the last column is what I want to find. I have two options. Option number one, build a monster that can actually hold this thing and run my machine learning on this. What is the problem? Number one, that monster is going to be a lot of cost. And once I build it, I do the analysis in the first half an hour, and then next 1 year I'll have to wait for the next analysis to run. So I'm losing a lot of money because I have to really make good use of it, right? So that's the problem. Secondly, if I fail somewhere, I have to start again. It's a huge computing cost. So what people said is, okay, if I have 5 terabytes of data, let me split it on 1,000 machines. Each machine now only has 5 gigabytes of data. Cool. 5 gigabytes is peanuts nowadays. It can fit in a RAM. You have 8 GB RAM, right? So you can fit it in a RAM. So 1,000 machines, 5 gigabytes, run the analysis. Now what complexity does it add? First thing, one of the machines may fail. I am looking at 1,000 machines, right? One of them may fail. So I need to have a failover mechanism. What they said, okay, put it in 1,000, ensure that every data is copied into other machines. Not only in its primary machine, put it into other machines. So that if it fails, I have a backup to access it immediately. Great. Second thing, I have in 1,000 machines, there are two options. One is, there is a program that needs to run. One is send each of these data sets to this program, run it, take the result, send it back. Send the second thing, run it, take it back. Third thing, run it, take it back. Or send this program to all those 1,000 places. Which is easier? You send the elephant to rabbit or rabbit to elephant? Rabbit to elephant, right? Your program is 1 kilobyte, your data is 5 gigabytes, you better send the program. So your program now goes to multiple data sets and comes up with multiple results. So you have to write the program in such a way that it splits and goes and collects the results. Then you need to write another program to combine those results. Right? There are 3 innovations that you need to do. Given a data, figure out how to distribute, then figure out how to split your program, figure out how to combine them once you get the result. And I have trivialized it to no bounds, but this is the big picture. And Dr. Sridhar is going to walk you through the entire details of this, but when people say big data, what they are doing is, there is a file system, Hadoop file system, which is nothing but splitting this into those 1,000 things with enough redundancy. Then there is a map reduce paradigm, where in map, they actually split the program and get the results. In reduce, they reduce all those results into one single set. That is the big data. That's why it makes sense. That's how it should be done. That's why it's now taken over by people. Yeah, if you want to deal with 1,000 terabytes, this is the way to do it. And now there are many things, how do I actually make it really simple for the end user? Those who just know SQL programming. Let us devise a way in which SQL-like programming can be done on this data. They came up with that, that's called Hive. Those who know Perl scripting or PHP, let's devise a scripting environment, they call it Pig. You learn all that. But the point is, okay, those are details. At a high level, if I have nano data, search is a problem. If I have huge data, engineering is a problem. Both make the original data science problem tough. Unstructured data makes it tough. Big data or nano data make it tough. High dimensions make it tough. Whenever you look at a problem, you understand this. What is good data now? If 5 is very bad, 5 billion is also very bad, somewhere there is a sweet spot in between. Well, that changes with technology. As I said, in 1980s, when computers were with 32 KB RAM or something like that, 500 records is a huge thing. Today, let's talk today's thing. Laptops have around 4 gig. I think 4 is not unusual. And 2 gigs are eaten by Windows, right? So you have 2 gigs left. Each cell, it's a good estimate, 100 bytes. Each cell is 100 bytes. 2 gigabytes is 10 cells is a kilobyte. 10,000 cells is a megabyte. Million cells, 10,000 thousands. 10 million cells is a gigabyte. 20 million cells is what a good data. So if you have 100 columns, 20 million, 2 million, 200,000. 200,000 rows and 100 columns is good data. You can handle it in your system. You have a powerful system, you can increase it. It is not uncommon to have 64 GB RAM also for a server class machine. So that is 10 times or 20 times that. So the beauty is 4-5 million records with 100 columns is also regular data nowadays. The fourth, they call it the velocity. Now, traditionally what do you do in a data analytics, data science thing? You are getting some data, store it, order, store, and then someone actually puts it in a warehouse. And then you analyze, you do your cool machine learning here and use the patterns. Does this framework work for fraud detection? Because the data comes, ATM machine, they have withdrawn, I know. And then after a week or so, entire thing came into a warehouse. I analyze after a week, and then after 3 weeks, I say, hey, you know what, 3 weeks back someone looted. And I can tell with 98% certainty. It doesn't work, right? So I need to really change the gears. What do I do? As the data is coming, I should look at it and say, hey, boss, this looks like a bad pattern, fraud. Go, check it out. Send the engineer. Failure. It's a very important thing. In the operation, if something is failing, after 3 months knowing that it's failing, is I have to tell as it is happening. If you have to do online analysis, engineering is a lot more difficult than offline. Customer value, which customer is likely to be, I should give extra discount, can be done in batch. So there are some problems that are batch problems, some problems that are online problems. If I have to do online and streaming analytics, obviously you can see that it makes the problem more. Okay. At this point, I want to make a very important distinction here. Whether it's big data or streaming data, if I have to do analytics on that, it's immensely more complex. But most likely, what one normally does is, you take some data, extract the patterns. Now, in real time, you recognize whether that pattern is there or not. You don't create the pattern in real time. It's very, very complex. So people do that. There's a whole research happening in stream analytics. But what I'm saying is 90% of the business applications identify 1,000 patterns of fraud, integrate it into your process flow. As and when that pattern appears, highlight. But it's what you miss some. Learn from that, recreate. Learn from that, recreate. So you keep updating your rules, archiving some rules that are not relevant anymore. And it's a process that's ongoing. So there is a batch engine that creates the rules, it is supplied here, and it is analyzed. Same thing with big data. And the last one, a couple of them, I want to give that make the problem more complex. Missing, if there are a lot of values that are missing, I can't ignore them. If there is a data point that's missing, what can I do? I can ignore it. Yeah, one attribute, age is not there. Why do I build the model? Just drop it, man. Only one record. Now let me build the model on 4,999 records. I'm okay with it. But if 2,000 of them have missing values, I can't drop them all. What will I do? I have to guess some values. That's the process. When I'm guessing, I'm polluting the data. I have to guess, super guess, and refine my guess. There's a whole lot of things. So outliers, missing values, all these things make the problem tougher, pre-processing tougher. Yeah, last one is a bit difficult to guess. If the data space is very complex, there's a pattern here, here, I have to split it like that. Most models fail to capture all of them. It's a very, very complicated thing. Most of the real world problems, this is, some left-handed drivers behave in a very different way. That's a small subset of the entire data. You won't be able to guess it looking at the data, but there will be some really hidden insights somewhere. There are some major patterns which are easy to find, but all these minor patterns are extremely difficult to find. So when you are engaged with a customer, the first few patterns you can give very easily, and later every additional pattern takes a lot of effort. Okay. And one more thing that I didn't mention, which is not technical, that I find is the controversy quotient itself makes the problem very complex, So that is essentially what makes a machine learning or a data science problem very complex. Okay. Time for a 5-minute stretch. But before that, I just will conclude what we learned from first part. We learned models are important. And we learned there are 3 major types of models. All can be set up as search problems. And we learned there are multiple types of searches in machine learning. And there are multiple types of outputs. And we figured out how to, what kind of outputs makes best sense is something that we have to figure out. Then we actually looked at a framework. We said we'll start with a definition. We'll figure out what type of problem it is. And then we will actually look at what kind of error metric we have to use. Define them before we start a problem. And we also learned that we have to split the data to ensure that our models work on unseen data. Then we actually said, okay, high dimensionality and large size of data, unstructured nature of data, speed with which the data is coming, if we have to do the analytics in real time, and missing missing and outlier kind of data, all these make analysis problem and data science more tougher on such data sets. So we learned what kind of data sets make it tough, what kind of data. So we also learned that a structured, small dimensional, so your dream come true is if you are given an Excel data set with less than 50 attributes and no missing values and static with around 100,000 records. Bingo, you probably need a couple of hours to do the entire model.